All right then, so 3.2, these are the all questions for the higher paper now. And here's your formula sheet. As always, a couple more equations for the higher paper, and then your multipliers and your prefix down the bottom. These we're going to be using today in a question, and not so much these, I don't think. So, first question. We've had a similar question in the foundation paper, but there is more demand on this question. So the first question for 2 marks, calculate the annual energy output per meter squared. Now we did that in the foundation, and to do that you just get there, so the roof area per meter squared there, you get 7 meters squared, which will produce this much energy, or estimated this much energy. So how much per panel? Well, how many times does 7 go into that? And it's going to be 120 kilowatt hours there, for 2 marks. Next question then, describe, let me just straighten this up a little. There we are, that's better. Describe the relationship between the roof area, so this column, and the estimated annual energy output. Well, as it goes from 7 to 14, it goes from 840 to 1680, so that it doubles. And if we go from 14 to 28, which doubles, 1680 doubles to 3360. So it's proportional, it's directly proportional. On a graph, that would look like that. It'd be a nice straight line. As one doubles here, the other one's going to double on this side. And that's what directly proportional means. Okay then, a householder installs, so again, we had this in the foundation, but it was split up into many parts. This time it's worth 4 marks. So we have to do it all ourselves. So the first thing I did was to see how much energy was generated, or how much energy is estimated at 28 meters per meters squared. So at 28, this much energy is estimated, but they only use this much. So first of all, I want to see how much is spare. So that's 360. Now they can sell that back to the electric company, and it says all this in here if you was to read this, but I want to make this video quite quick. And it also gives you all this information. So the export tariff back is 5 pence. So that's the first thing we're going to do. So 5 pence for 360 units is going to give us £18. Then we need to see how much energy we've saved on the energy that we've used, which is 3,000. That's what they've used. And that's 16 pence on every bit that they use by here. Look, 16 pence on every bit that they use. So I'm going to calculate that, and that gives me £480. And then I've got this FIT, which is the feed-in tariff. And that means for everything that's generated, you're going to get 12 pence. So it was estimated that it would generate 3,360. So we're going to get 12 pence for every one of those. So that's £403. And then you just add them all together. Okay, so it comes out to be £901.20. For 4 marks, I think that's very doable. This question is from foundation paper as well, so I won't spend too much time. It just says, why can't you really claim this? Because hours of sunshine vary, the angle of the panel on your roof will vary, and also the direction the roof is facing will vary. Then we come to a 6 marker. Consumers rely on a continuous supply of electricity from the national grid. Describe how the national grid supplies a reliable source of energy, a supply of electricity, and how it's efficient as possible. So I'm going to talk about this, and then the last 2 bits at the end then. It was all about efficiency. So I've said something along the lines of, the national grid consists of a network of power stations, transformers, substations, and power lines, all joined together, supplying electricity to consumers. That's probably going to get me a mark for telling what it is. I'm going to say supply and demand is monitored, because it is. You've got people monitoring supply and demand. And then at times that a power station fails, so when a power station breaks down, we can get electricity from another part of the national grid. So that's going to get you 1 mark, because they're all connected together. It's an advantage of the power of the national grid. But at times of peak demand as well. So if we're all watching EastEnders at 6 o'clock, okay, there's going to be a peak demand at 6 o'clock, and we may need to get electricity from another from another power station, or sometimes if we've got, say, let's say Cardiff is going to hold the next Olympics, and the Olympics is going to demand a lot of electricity, we may have to import from abroad. And then I'm just going to talk about the efficiency then down the bottom. Transformers are used to step up the voltage. Now, if we step up the voltage, we're going to reduce the current, and we're going to reduce that power loss as heat in the cables. So that's your 6 marks. Next question is all about reading graphs. Oh no, it's still connected. This one, we've got to watch out for these units, because we've got terawatts, we've got gigawatts, we've got megawatts going on. So it's just worth noting there. The question's relatively easy apart from that. It's just a simple efficiency question. It's using information and an equation from page 2. Let me just show you that equation so that you know I'm not making it up. So the efficiency equation there is useful over total, okay, times 100, because it's a percentage. Where am I? I'm on the wrong page. So that's what I've done. So I've written that there, and then I've just got the figures from the table then. So what is the useful energy? Well, I don't know that yet. I've got my wasted energy, and I've got my maximum demand, my total energy. So my maximum demand, that's what it says there. So my maximum demand is 63 gigawatts. Now, a gigawatt, if we look at the front page again, a gigawatt is times 10 to the power 9. That means there's 9 zeros, whereas a megawatt has only got 6 zeros after it. So I'm going to have to convert there. There's a little bit of converting to do. So what I have done, I've turned 63 gigawatts into 63,000 megawatts. Hope you can see what I've done there, because there's 1,000. There's 1,000 megawatts in a gigawatt, if you know what I mean. So I'm going to convert that to 1,000. Then I'm going to find the useful. Now, to find the useful, I got the total megawatts, because I've already converted it now, minus my wasted. My total losses there is 1420 megawatts. That's getting wasted. So this is going to give me, sorry about the right number here, 61580 is now my useful. If this is getting wasted, and this is your total, 63, then subtract the wasted from the total, and it's going to give you a useful. Now I use the equation useful over total. So my useful was 61580, and that's going to be over the total times 100. This is pretty efficient, okay? This is 97.7% efficient. 3 marks. Again, relatively easy so long as we're going in looking for these things. They will throw these things at us. I'm going to deal with a terawatt now in a bit, because it's here. It says you calculate the annual mean power. They even give you the equation this time, but you'll find this at the front, I think, power energy transfer. No, you don't. Let me just check that. Power energy transferred. Yes, we do. There we are. They've just rearranged it for you. Okay, so no rearranging needed there. Where are we? Let's go back down here. So, again, if it's 300 and, where is it, gigawatts. All right, so it says to calculate the annual mean power used. So the annual mean power used in gigawatts. Well, let's have a look what it's there. So the annual mean electricity energy used in the UK is 360 terawatt hours. I need to convert that now to gigawatts. If I look at the front, okay, so a terawatt's got 12, a gigawatt's a step down. So again, I'm going to need to add 1,000 or 3 zeros now to whatever I've got. I'm all over the place here. Sorry about this. So I'm going to turn that into 360 terawatt hours is going to be the same as 360,000 megawatt hours, because gigawatt hours, sorry, because I'm in gigawatts now. And then the hours is there. So I've just stuck that over the time. So I'm just using the energy. Remember, a kilowatt hour or a terawatt hour or a gigawatt hour is just a unit of energy here. And then we stick it over the time, which is that many hours, and it gives us 41.1 gigawatts. This one is, and notice just, this is the end of the paper here. This is the end of the higher paper. So these questions are going to be a fairly high demand question. And these are no exception here, okay? For 2 marks, you need 2 correct answers. Now, if this was the end of the paper and you were in a rush, take a punt, a guess into at least. But this is going to take a bit of working out. At maximum demand, there is spare capacity of 16.9 gigawatts. How did I work that out? I looked at my output capacity, which was 79.9. I'll just show you where that was. My output capacity there is 79.9. That's what it's capable of. But it only generated 63. Okay, the maximum demand was 63. So what this is saying is at maximum demand, there's a spare capacity. It could have gone to 79.9. Well, 79.9 minus the 63 is actually 16.9. So this statement is correct. Okay, it could have generated this, but at maximum demand it was this, so there was this much left. So that's correct. Maximum demand is equivalent to 85% of total capacity. So your maximum demand, 79.9, is the equivalent of 85% of total capacity of 63. Well, let's have a look if that's right. So what I've done, I've said 85% of 79.9 needs. So I've gone to 10%. I need to find 85% of that to see if they're right up there. So I've done 10%. I've come down to 1% there. 1% of 79.9 is 0.7999. And to make sure, if you want to do that on a calculator, you just simply divide 79.9 by 100, and you get that. And then if you times it by 85, you're going to come up with 85%. Well, 85% of 79.9 is 67.9. It's not 63, as it was suggesting. So this 63 is not 85% of the 79.9. Okay? It's not that. So this is wrong. Again, it's a lot of working out, I know, but it is the end of the paper. The difference in minimum demand between summer and winter is approximately 10,000 megawatts. Now, be careful with this. You've got to look at the graph now. The difference in minimum demand. Now, minimum demand, where they are lowest. So you can see that demand is low here. Try not to get confused with the gap, the minimum gap between the two lines, okay? It's easy to get confused between, oh, I'm looking for the smallest gap between these two lines. It's not that at all. It's when the demand is low. A national grid demand. When this number's low, that's what we're looking for. Now, the difference when it's the lowest, you can see that in the summer, here, this dark line, it's around 25,000. And then in the winter, its lowest is around 35,000. And the difference between them two is 10,000. So this is correct. The time, so now that I know that, but I'm going to go through these anyway because I feel that I should. The times of peak demand in summer and winter are exactly the same. Well, let's have a look at that. So peak demands, well, they're not the same at all, are they? Okay, there's obviously a difference there. And then the difference in maximum demand between summer and winter is 15,000. Let's have a look. Oops, didn't want to do that. So 15,000, and it doesn't quite get there, does it? Because that is around, that's not even 3 boxes, and each box is worth around 5,000 here. So again, that is incorrect. And going back to that last one, just in case you didn't know what I meant, that the peak demand in the winter, I would say, is around about 6 o'clock, and the peak demand in the summer is slightly shorter because there's a difference. It's still light at 6 o'clock in the summer. That was a tough question. Okay, so another bit of information on climate change. They're going to throw something like this in. This is one of those stacked bar charts where you've got keys telling you what these are. So you've got oil at the top, and then you've got renewables and coal and gas down the bottom there. And it's also giving you some quarters. So the first quarter between January and March, April and June, so on down here. Okay, so now that we know that, we can have a look at the question. The question A is quite easy for 3 marks, I think. Just asking for a trend. And I've said there's a general trend, downward trend in fossil fuels. So I've said significant decrease in coal, increase in gas, and a stable use of oil. So we've got to look at fossil fuels. This is why I haven't mentioned any of the renewables or any any nuclear really, okay? So fossil fuels only. Let me just check the graph so you can see what I mean by this downward trend. Significant decrease in coal. Well, coal is the really dark shaded, and you can see that coal, even though it spikes there, there's a downward trend. The use in gas is pretty constant. I've said, in fact, it does increase, doesn't it? The use of gas there, and I think I've said that there. Increase in gas, and then a stable use of oil. Or which one's oil? Oil is the sort of grey area here, and the grey area is, it's fairly constant. The use of nuclear power fuel in the production of electricity between Q1 2003 and 2016 remained roughly constant. Suggests possible reasons for this. This is coming from your sort of outlook. I said nuclear power stations run all the time, so it's not going to fluctuate because they're 24/7. They're just constantly running, and no new nuclear power stations being built within that time. Okay. Then the production of electricity from renewable sources remained roughly constant between Q2. However, there was a reduction in contribution of wind and a slight increase in solar power there. So I've just said it's less windy in 2006 and there's more sunshine in 2016. 16 I meant by there. And that's your 2 marks. Don't overthink that one. Then the last bit of the question is a beast. There's lots of information going here, okay? It is just knowing how to pick this information out. Calculate the targeted percentage drop in CO2 emissions from all sources between 1990, which was 3900 million tons, and the end of 2022. This is the hardest bit, where it was 2544. The hardest bit is recognizing, because there's so much going on, there's so many numbers that you need practice in identifying what's going on here. Okay, so percentage drop is change over original times 100. Okay, this is going to be drilled into us. Change over original times 100. Okay, so what is the original? 1990 is 3,900 million tons. And in the end of 2002 by year, it was 2,544 million tons. So this is the original number. Let's calculate the change now. So this minus this is going to give us our change, 1356. So I've put 1356 on the top of 3900, which was our original, times 100 is 35% for 2 marks. This last question was solid, so I'm just going to go through it because, again, it's the end of the paper. I needed to look at the mark scheme for this. Good progress is being made in electricity generation sector because 40% leads to 50%. Okay, your 40% here leads to the 50% by the end of 2027. However, because the question says the government's will target emissions, so what is a comment on the progress being made? I've said, however, there are other sources of emission which need to be taken into account. So not just emissions being released by the power stations, but domestic heating and vehicle emissions, people driving around in cars, things like that. Really hard question, though. Question number 7 now is from a triple paper, so I've only got it on for the one question, really. So I'm going to go through it because this will apply for triples, but I'm not going to answer that last question because this is mainly a triple question. You haven't got that equation. So, in fact, we can just look at this graph. This graph is telling us that there's a power output for a wind turbine here, and the wind speed needs to be, as the wind increases, you can see that, you know, the cut-in speed, and it'll tell you in the blurb here that the cut-in speed is the speed at which the turbine starts spinning. So sometimes you'll be out on a sunny day and you won't even see these turbines spinning. That's because the wind speed is very low. It needs to be at least 3.5 there for that turbine to start turning. And then you can see as it increases and then we've got a maximum sort of cut-out speed at the top there. So gives you another graph here where wind speed is telling you it's going up here, the wind speed, and then the time of day across. Now, someone claimed that the wind power is always a useful backup at times of high demand between these times and these times. Explain whether the information in the grid supports this claim. I said it does not support this claim because you can see clearly here that this is quite low. And remember us talking back to that first graph, that cut-in speed must be 3.5. It's only just above that. And even when it comes to between 4 o'clock and 8 o'clock by year, 1600 hours and 2000 hours, it's even lower. It's not even meeting that cut-in speed. So I've said between these hours, the wind is very low. So I've picked out, because this is worth 4 marks, so I need to get some data in there. I need to be picking out and showing the examiner where I'm getting this information from. Between this and this, wind speed is low. Okay, I said output is so low that the cut-in speed must be this. So between this time, the turbine wasn't even on. And this will probably get you the 4 marks there. Okay, and like I said, I'm not going to go through this because I think probably Mr. Mulroy will run through the whole paper with you. So I'm going to leave it there, 20 minutes. A really tough paper in my opinion. They're tough, wordy questions, but you're going to get that with 3.2. This is the sort of stuff you can expect. Not a lot of memory required here, apart from the national grid stuff, but a lot of data reading and just wordy questions. Okay, good luck.